Getting the best from Chemistry Explained needs you to participate. So write notes, complete tasks on paper or tablet. Pause and control the pace at which the lesson goes. Crucially, complete the tasks when prompted. That means pausing the lesson, taking your time, thinking the problem through. Only when you're ready, continue. Correct your work before moving on to the next slide. So, the haloalkanes. Naming of haloalkanes follows the same patterns that you've met with alcohols and alkanes. So I've got 4 examples here. I'd like you to pause the video and make your best effort to name these 4 molecules. Okay, so let's just run through the correct answers, going from left to right. So 1-bromopropane, straightforward I hope. Centrally here we have 1,1,1-trichloro. So we're going to number these carbons here 1 and 2, so that's ethane, but on the first carbon, carbon number 1, we have 3 chlorines, but we need to position them all as well. So we need to position all 3 chlorines on the first carbon. So that's 1,1,1-trichloroethane. Moving on, 2-bromopropane, carbon 1, carbon 2, carbon 3, so 2-bromopropane. And then here we have 1,3-dibromobutane. Now, you may have written 2,4-dibromobutane, but the rule of using the lowest possible numbers, so 1,3 in preference to 2,4. And di, of course, for the 2 bromines. Tri for the 3 chlorines, and we don't say monobromo, we just say bromo. So just as alcohols, the structures of alcohols were classified, similarly for haloalkanes, exactly the same idea. So could you look at these 3 examples and classify them as primary, secondary or tertiary? Pause the video and do that now. Okay, so we are interested in the numbers of alkyl groups attached to the halogen carrying carbon. So here's the halogen carrying carbon, and we've got 1 alkyl group, so that's primary. Centrally here, this here is the halogen carrying carbon. It's got 1, 2, 3 alkyl groups attached to it, so that is tertiary, and it's obvious, I hope, therefore, that here we're interested in how many alkyl groups attached to this halogen carrying carbon, and it's 2, so that is secondary. So the reactions of the haloalkanes are substitutions. There's only one that you need to know the detail of at AS. There are more in Year 13 chemistry. It's a hydrolysis by aqueous alkali. So here we have the haloalkane turning into the alcohol, and the halogen leaves as a halide ion. So let's look at an equation. So here's bromoethane, a hydroxide ion. Could you complete that equation now? So looking at the complete balanced equation, we see we will form ethanol, and the bromide ion leaves. You'll see that the equation is balanced for charge left and right. -1 overall on the left hand side, -1 overall on the right hand side. Very handy to keep checking for a balancing of charge. However, sometimes you are asked to use not a hydroxide ion, but the full compound sodium hydroxide. Could you complete that equation? Pause and complete. So if we have sodium on the left-hand side, it must appear on the right, either as sodium bromide, or it could be accepted just as a sodium ion alongside a bromide ion. But that is our complete balanced equation. If sodium appears on the left-hand side, it must appear on the right. What are the conditions? We need to know the conditions for organic reactions at A level. The aqueous alkali should be warm. Very simple. So, I'd like to give you a problem. Identify the organic product of the aqueous alkaline hydrolysis of 2,2-dibromopropane. So identify the organic product. Pause, think it through, come up with your answer. So, here is 2,2-dibromopropane, and here, of course, would be the product. Both bromines are substituted for by a hydroxide ion. So could you write that now, those displayed formulae, could you represent those as structural formulae, please? So a little bit of confidence needed in writing these. If we look here, it's CH3, CBr2, CH3. So there's our representation of the 2,2-dibromopropane. And for two hydroxyl groups, exactly the same, except we need a bracket around the hydroxyl group to show that it's not separately bonded oxygens and hydrogens. So we bracket the hydroxyl group, but there are two of them. And we needed it balanced. So there's 2 hydroxide ions needed from 2 sodium hydroxides. So we get 2 sodium bromides to balance the equation. Correct your work, please, and take note of any errors that you have made. Now, the substitution reactions of the haloalkanes have a mechanism on the specification, and it's a nucleophilic substitution mechanism. So you need to know what a nucleophile is. You will possibly have met the term before. It's an electron pair donor. A bond is formed by the donation of an electron pair. So let's look how this applies to a haloalkane. So I'm starting with a bromoalkane, my preference. And I'll bring in a nucleophile. Forgot to mention that the specification only refers to the nucleophilic substitution reactions of primary haloalkanes. You will see in other textbooks, other than the OCR A-level textbook, you will see secondary and tertiary haloalkane substitutions. That is not required in the OCR specification. So I'm sticking solely to primary haloalkanes. So the reactivity of the haloalkane is because of the polarity of the carbon-halogen bond. So if I bring in a nucleophile, such as the hydroxide ion, the nucleophile, you would indicate the presence of a lone pair of electrons, because we need a nucleophile to have a pair of electrons to donate. So make sure you have marked on your nucleophile a lone pair of electrons. That pair of electrons attacks the carbon-halogen bond. Could you pause the video and write in the correct 2 movements of electrons using a curly, or using 2 curly arrows? Could you pause and do that now? Okay, so check whether you've been correct. The lone pair of electrons from the hydroxide ion approaches or attacks the electron deficient, the carbon delta plus, and that causes a movement of electrons from the bond to the bromine, which we indicate with another curly arrow. So if you recall, a curly arrow indicates a pair of electrons, the movement of a pair of electrons. So we've got 2 movements. The electron pair from the bond go onto the bromine, and the lone pair of electrons on the hydroxide are going to form a bond with the carbon. So could you predict the outcome of those two electron movements? Can you draw the structure that results from those two electron movements now? So hopefully you have drawn something like this. If not, correct it. Instead of a lone pair on the hydroxide ion, it's now forming the bond pair here. And what was a bond pair here now appears on the right hand side as a lone pair of electrons on a bromide ion. Again, we're balanced for charge. The bromide ion is balancing the hydroxide ion in terms of a negative charge. So that is our model for nucleophilic substitution, and other than varying the nucleophile, it does not vary. So, simple problem, show the nucleophilic substitution mechanism for the formation of ethanol from iodoethane. So pause and put in the necessary components of that mechanism. So if I continue, first of all, of course, we need to put in the bond polarity, often forgotten. We need the bond polarity to explain why the hydroxide ion nucleophile attacks the carbon, because it's delta plus. That induces a movement of an electron pair onto the iodine, so we need to balance the right hand side with an iodide ion. That is a common error. The iodide ion should have marked on it, as I'm indicating with the laser pointer, a lone pair of electrons. If you didn't get that right, I suggest you just scroll back and do that problem again. So one aspect of nucleophilic substitution in the specification is the different rate at which the chloro, bromo and iodo alkanes react. A simple test tube experiment is described in the specification, but you are expected to reason. The reasoning starts with the idea that the halogen, the larger the halogen, the longer the carbon-halogen bond. And if the bond is longer, for instance carbon iodine compared to carbon chlorine, if the bond is longer, then that bond has a lower bond enthalpy. If that bond has a lower bond enthalpy, it is easier to break. And therefore an argument based on bond length would be that the iodo alkane would have more rapid reaction with nucleophiles. However, you may want to compare the rate of nucleophilic substitution and explain its varying rate on the basis of bond polarity. Here you see that the carbon-chlorine bond is more polar than the carbon-iodine bond. Does that affect the rate of reaction? Well, although the bond polarity on the chloroalkane is greater, as the halogen is smaller, you should have seen or carried out the experiment yourself and found that iodoalkanes react more rapidly than chloroalkanes. So the conclusion is that bond enthalpy rather than bond polarity is the deciding factor. Now, if you have done this experiment in the laboratory, then you can probably skip the next couple of slides. But if you haven't, or you just want to recap, just stay online with me. So the test tube evidence on the rate of hydrolysis of the varying haloalkanes is based on the formation of a silver halide precipitate. because that will give you a measurable endpoint. So silver ions and halide ions form silver halides, which are insoluble precipitates. You will, in the halogens topic, you will look at the different colours, but I'm going to move on from that. So the method would be that you add the haloalkane to a suitable solvent, ethanol, universal solvent, and you control the temperature, probably in a water bath. You add drops of aqueous silver nitrate and you start a timer. The aqueous solution, we haven't got hydroxide ions there, but the water itself will act as a nucleophile, so that will also produce the hydrolysis of the haloalkane. And you observe the formation of a precipitate, and when you get a certain amount of precipitate, which you will decide as an experimental, you stop the timer, and then you repeat across the various haloalkanes, and you've got a comparison in terms of time. I'm going to move on. So typical results would be an observation at 5 minutes perhaps. Chlorobutane, cloudy white suspension formed. Bromobutane, you get a thin cream precipitate, and iodobutane, a thick yellow precipitate. And that is meant to indicate that iodobutane undergoes hydrolysis faster than bromobutane, faster than chlorobutane. And that is justified not on bond polarity, but on the length of the halogen carbon bond, the strength of the carbon halogen bond. The longer the bond, the weaker the bond, the faster the hydrolysis. And if you look at the mechanism, you can see that that carbon halogen bond has to be broken. So one application of haloalkane chemistry is in its involvement in ozone depletion. So organohalogens, known as CFCs, chlorofluorocarbons, are involved in the depletion of ozone trioxygen in the upper atmosphere. Now, ozone is an important molecule because it absorbs harmful ultraviolet light and prevents it from reaching the Earth's surface. CFCs such as CF2Cl2 are known to deplete the concentration of ozone, and you can look up the work of Molinari and Farman, etc. in that if you wish. The first step is a homolytic fission of that CFC. So could you write an equation for the homolytic fission of a CF2Cl2 molecule? So could you complete that equation? Pause the equation, pause the video, think it through and write the product side. Okay, well, if you remember, homolytic fission involves the breaking of a covalent bond with the sharing of the pair of electrons equally between the two particles formed. So we form two radicals indicated by the dot. That is required in OCR A specification. That is an unpaired electron. So these dots are unpaired electrons. They were a pair of electrons forming a bond between carbon and chlorine. But why are we forming a chlorine radical and not a fluorine radical? Pause the video, think it through. Why a chlorine radical and not a fluorine radical? So here's the simple answer. Carbon-chlorine bonds are much longer and therefore weaker than carbon-fluorine. So the chlorine radical will be formed. But what are the conditions needed for this initiation? Well, articulate it, speak it out loud. Of course, it's ultraviolet light. The energy source for breaking the carbon-chlorine bond is ultraviolet light. So this chlorine radical reacts with ozone, forming dioxygen. So the chlorine radical reacts with ozone. One of the products is dioxygen, O2. Could you complete and balance the equation? So we get dioxygen and a radical formed between chlorine and oxygen. An unpaired electron is indicated. Now, propagation, of course, we know that the numbers of radicals is maintained going from left to right. But we need to regenerate the chlorine radical. And this is done by a reaction with an oxygen atom. Could you write the appropriate equation? So continuing, the chlorine oxygen radical reacts with an oxygen atom to regenerate the chlorine radical and reform dioxygen. Okay, so if we look at combining the two steps to produce an overall reaction equation, have a go at that, and then I will show you model my method. So pause the video and come up with one overall reaction from those two steps. Okay, so how I go about this is to just to do something quite visual. I draw a line here separating out the reactants and the products, and then I eliminate reactants that also appear as products, and then that will leave me with an ozone and an oxygen atom and two dioxygens on the right hand side. So my overall equation is like so. One point to make is that the chlorine radical is classed as a catalyst, and that's because it is regenerated. So the two propagation steps starts off with one chlorine radical and using up one chlorine radical in the first step, but generates one chlorine radical in the second propagation step, and therefore the numbers of chlorine radicals remain unchanged. And this is why a small concentration of chlorine radicals will have a very ongoing and large effect on the concentration of ozone. So nitric oxide is an example of another radical that depletes, is known to deplete or catalyze the breakdown of ozone. Nitric oxide is a radical. It has an unpaired electron. If it collides with an ozone molecule, could you predict the outcome of that reaction? So I'm going to reveal the products of that. NO2 is formed and dioxygen O2. So NO2 is also a radical. So the next propagation step will involve the nitrogen dioxide radical and an oxygen atom. Could you predict the products of that propagation step? So if I reveal the products, we regenerate nitric oxide. We're regenerating nitric oxide. So nitric oxide, NO, is not used up. What is the overall reaction? Pause the video and deduce the overall reaction. Here is the overall reaction, exactly the same method as previously. Draw a line, take out those things that are on the left and the right, and I'm left with ozone and an oxygen atom and 2 dioxygens. So nitric oxide catalyzes, that is, the propagation steps regenerate the nitric oxide. So the nitric oxide is regenerated. Exactly the same for the chlorine radical on the previous example. Hence we have an immense effect of a small concentration of nitric oxide or chlorine radicals. So for my final slide, just the obvious statement that to consolidate you need to practice, you need to find problems from whatever source you have available to you, but those sources which have comprehensive answers are the best. So attempt the problems, check your answers, move on when you are being consistently accurate and complete in your answers. Choose the next topic that you think for you is the one you need to focus on.